So we have a candle burning at a constant rate of 1.3 inches each hour. Of course, if the candle's burning, it must be getting smaller. So G of T represents the length of the candle in inches, and T is the number of hours elapsed since the candle was lit. So the candle starts out big, it's losing 1.3 inches each hour. All right, good. So explain what the expression G of 1.3 minus G of 2.7 represents. So the first thing to note is, what are these numbers inside here, this 1.3 and this 2.7? So the 1.3 is a value of T, because see, it's sitting here like this G of T, and T represents the number of hours since the candle was lit. So G of 1.3 would be the height of the candle, the length of the candle, 1.3 hours after it was lit. And then we're subtracting off of that the length of the candle, 2.7 hours after it was lit. And so this whole expression here represents the change in the height of the candle, or the length of the candle, from 1.3 hours since it was lit to 2.7 hours since it was lit. And actually, it's not quite that, because notice here we're doing G of 1.3 minus G of 2.7. So it's really, this is going to be a positive number because it's going to be higher. It's going to be G of 1.3 will be greater than G of 2.7. So this is actually the absolute value of that. So it's the absolute value of the change in the length. So we'll just kind of put that into the side. In other words, the change in the length is going to be a negative number because it changes, because it's the length of the candle is decreasing. But this number here, this expression is going to give us a positive number, so it's the absolute value of that. Okay, explain what the solution to the equation G of T equals 4.5 represents. So the first thing we want to realize is, what is this 4.5? Well, it's an answer to G of T, and G of T stands for the length of the candle in inches. So that 4.5 is the units of that would be inches. So what it's asking for is the solution to G of T equals 4.5 would be is the time in hours since the candle was lit, in which the length of the candle is 4.5 inches. In other words, the solution would be the value of T. So the solution is a value of T. So at what time is the length of the candle 4.5 inches? Okay, explain what this equation means. G inverse of 2.398 equals 3.44. So we need to think about the inverse function. So the function G takes a number of hours and outputs the length of the candle. But the inverse function is going to do the opposite. So it's going to input the length of the candle, and the output will be the amount of time in hours. So this input here to the inverse function is a length of the candle. And this number here, the output of the inverse function would be amount of time in hours. And so what this equation means is that 3.44 hours after the candle was lit the length of the candle. Candle was 2.398 inches. Very precise measurement there. Okay. Suppose that the candle is 3.1 inches long after having burned for 2.9 hours. What was the length of the candle before it was lit? Okay, and so here we have to go back up into the beginning statement of the problem to see what is this rate of change here. So we know that it's burning at a constant rate of 1.3 inches per hour. So using the fact that it's a constant rate of change is going to allow us to solve problem D. If it weren't burning at a constant rate, then we'd have to have some idea of what this rate of change meant, right? But since it's a constant rate of change, we know that this is a linear function, and so we have that. So in other words, we know that g of t is equal to mt plus b, and we know our rate of change is 1.3 inches per hour, but it's decreasing by 1.3 inches each hour, so it's going to be a negative 1.3. So in other words, g of t is equal to negative 1.3 t plus b. So that, I know, is what the function is going to look like. The thing I need to figure out is what is that b, and so that's what we're trying to solve for in part D there, because the question is that what was the length of the candle before it was lit, and that would be the value of b. So this is my initial value. Okay, so that if I can find that b, then that's going to be the answer to part D. Okay, so what I can do is I can plug in my known values. I can know that this is a value of g of t, and I know that this is a value of t. So I can use those two values and plug them into this equation here to get that initial value. So that number of inches is going to go here. 3.1 inches is equal to negative 1.3 times that t value, which is 2.9, plus b. And then I can solve for that initial value. So I know that b is going to be equal to 3.1 plus 1.3 times 2.9, just doing a little algebra there. So I can use my calculator to figure that out. 3.1 plus 1.3 times, oops, and so I get 6.87. Now what is this? This is a length of the candle, so this is in inches. So for this one, I have a graph that I'm given, and I'm supposed to, so it says all critical points, points of discontinuity, and points of inflection can be observed on the graph. So really, we're just trying to look at the graph and come up with some solutions here. Okay, so the limit as x approaches negative 6 of f of x. So let's go here to the function as x approaches negative 6. So if I look from the right-hand side, I can see that my function value is approaching 5. And as we approach 6 from the left-hand side, I can see that my function value is also approaching 5. So since my left and right hand limits are the same, the limit exists and it's equal to 5. Okay. What about f prime of 3? So I'm going to go over here to 3 and go up to the function. And notice that my function is linear, so the tangent line will actually be the same as that line. So I can compute that slope by just picking 2 points on my line and computing it. So I can see that I'm going to use these empty dots here on the ends of my line to compute the slope. So f prime of 3 is going to be equal to the rise over run, so 7 minus 2 over 4 minus 2. So that gives me 5 halves, right? Okay, and the limit as x approaches negative 2 from the left of f of x. So let's go over here to, as we approach negative 2 from the left, my function value is getting closer to negative 2. So as we approach x equal -2 from the left, my function value, the y value, is approaching -2. The answer there is -2. Now notice that the two-sided limit doesn't exist, because as we approach -2 from the right, we go off to infinity. So my left and right hand limits are not equal. But I can still write down what my left-hand limit is, so that's okay. All right, what about this one? Now notice what's happening here. It says the limit as delta x approaches 0 of this, and this should remind you of a, that should remind you of a derivative. So this is actually equal to f prime of -8 by the definition of derivative. And so if I look at what's happening at -8, I can see that my function has a local minimum. So the derivative value, the slope of the tangent line at x equal -8 is actually 0. So we've got that. All right, the next one says I want the limit as x approaches 4 of f of x. So if I look over here to 4, if I go in from the right side of 4, my function value is approaching 5. But if I come in from the left side of 4, my function of value is approaching 7. So my left and right hand limits are not equal to one another. So this one is a D in E. My left and right hand limits are not equal. Okay, then this says the derivative of f with respect to x at x equal -4. And so if I look at as x equal -4, so that would be, so that's the same thing as writing like f prime of -4. And so if I look over here at -4, I can see that it's linear. And so again, I can just write down what that slope is of that line. And so let's see here. So if I look at this line, I'm just going to pick 2 points on the line. So I'll just pick those endpoints of that line segment. I'll be fine. So I can do 5 minus -2 over -6 minus -2. Okay, so what does that give me? 7 over -4. So -7/4. Okay. All right, so that's just the slope there at -4. Okay. I feel like it's getting kind of cluttered up here, so I'm going to erase some of this stuff so we can see what we're doing again. Okay, well, let's go back to this one. F of x, limit as x approaches 2, f of x minus f of 2 over x minus 2. Again, that's just the definition of the derivative at 2. So this is the same thing as f prime of 2. And so if I look at f prime of 2, I can see that at that point, I have kind of a cusp sort of thing, but it's not even defined at 2. So since that's a discontinuity there, it's not continuous at 2. So and then also we have the left and right hand limits. The left and right hand slopes are not the same. So this is a D and E. We have some kind of a cusp thing going on, and then a hole also. So. All right, so the limit as x approaches 2 of f of x. Well, and another way we could say this is we know f of 2 is not defined. So since f of 2 is not defined, then that whole expression is not going to work. Okay, so what about the limit as x approaches 2 of f of x? So as x approaches 2 from the right-hand side, I can see that my y value is approaching 2. And as x approaches 2 from the left-hand side, I can see that my y value is also approaching 2. So since my left and right-hand limits are the same, they're just going to be equal to, they're both going to the y value of 2. So the answer there is 2. And this one, the limit as x approaches 0 of f of x. And I can see here on as x approaches 0, oh, sorry, I was using blue always from the right. So blue from the right, then my function is going to 3, and from the left-hand side, as x approaches 0 from the left, my y value is going to 3 also. And you can see it's continuous at 3. So since it's continuous, it's just going to be the function value. So that function value is 3. Then identify all the x values on the interval where f is not differentiable. Okay, so any of those places where we have kind of like a cusp or a discontinuity and those kinds of things. So if we're rocking along here and we can see that we have a problem here at x equal -6. Okay, then we're continuous, so we're good here. But when we get to this point, we have this kind of infinite discontinuity here at -2. And then we have another problem here at 2 because the slopes coming into 2 from the right and left are not the same slopes. And so we've got a problem there at 2. We also have this jump discontinuity here at 4, so we have a problem there. And the rest of it looks good. So those are the x values for which the function is not differentiable.